Hello everyone, my name is Daniel Ceverino. I'm going to talk about the bulge formation, especially through clump migration and compaction events, which are especially important at high-redshift galaxies in the VELA simulations. So this is one example here. So we are using the VELA simulations to describe all these processes. We can see the gas, wildly unstable gas disk, and at the center, we see the formation of the big bulge. So this is an alternative scenario for Gulf formation. It's more in situ scenario. So we know that major merges are rare, so we don't have enough major merges to account for the amount of bulge that we see around massive spirals. So we need something that is forming a bulge in any galaxy. And this is the process of wet compaction, mostly driven by violent disk instabilities and the migration of giant clumps. See one example here. These three galaxies were selected in these simulations to have a very quiet merger history. So here, less than 10% of the stars were formed through mergers above 1 to 10, I mean major mergers. They all form a disk, so you can see a disk young in all these cases, but 60% of the stars are actually in the form of a bulge at the center. So this formation of the bulge is not coming from material that is coming from outside. It's mostly internal process driven by instabilities. Now we're doing more large sample of galaxies in the VELA simulations. Here in the Sorotov et al., we were discussing the fraction of the bulge match that is coming from different components. So we found that 40% of the stars in the bulge at any redshift, for example, redshift 1, these stars in the bulge were formed in the bulge. They were forming in situ. Then 30% of the stars in the bulge in average came from the disk. Now, through the migration of clumps. So we see the formation and migration of one clump. Here, this is the gas surface density phase on. So we see the formation of one clump here, then is now orbitating around the center, and a few orbital periods emerge with the disk, with the bulge, merge at the center. The clump also carries some stars, but we found that only 30% of the growth of the bulge is coming from clump migration. And then finally, the other 30% are now the stars that came from other galaxies, I mean, through mergers. This is this red point, red area here. So the in situ origin of bulge was something very strong, and is something very insensitive to the feedback models. So insensitive to these clump lifetimes. Yeah, so other simulations with different models of feedback also produce clamps, but now these clamps are disrupted in a few dynamical, in a few free-fall times. So something very fast. In less than 50 million years, the clamps are disrupted in those models. So they don't migrate to the center. But still, in the simulations, they see the growth of a central bulge. So one example for Hawking et al. So here in this case is an isolated galaxy, in a galaxy within a box. So only a disk, initial disk. This was the initial gas profile. So after a while, after a few orbital periods, for any particular feedback model, they see an excess of stars at the center, mostly driven by the growth of the bulge. In this case, the growth of the bulge is mostly coming from the torques within the disk. So the disk is still marginally unstable, it's not axial symmetric. So then we see a loss of energy and angular momentum, and that drive inflow of gas to the center that builds the bulge in this isolated test example. Now in the cosmological simulation, we see at the same time mergers and compaction. And this compaction event, so this inflow of gas, is dominated or is driven by this wetness parameter. So this is just a ratio of two different timescales. First is the time scale for the star formation in the disk, and then the time scale is the time scale for this inflow of gas from the disk to the center. So if the star formation is very fast in the disk, so the gas first goes into stars before going to the center. So we end up with a disk, with a rotating disk with very little bulge. In the other scenario, if the inflow time scale is very short compared with the gas star formation rate, then the gas first goes to the center and then forms stars at the bulge. And this is what we see, the compaction. The compaction is basically driven by the dissipative component of the galaxy. And this parameter depends on these two variables. Epsilon is the efficiency of star formation, and delta is the most important one, is the mass ratio of the disk, is the disk mass fraction within a given radius. So if the disk dominates the mass with a given radius, we see disk instability and the inflow of gas to the center and the growth of the central component. So this is one example here in the VELA simulations. So what I'm plotting here is the gas surface density, phase on, and the bottom is the stellar surface density. What we see here is the evolution of the specific star formation rate. As a function, let's focus on the right panel, the surface density within 1 kpc that measure the growth of the spheroid. So we see that during the compaction era, the bulge is growing, the stellar surface density is growing by several orders of magnitude. So we see inflow of a lot of gas to the center, we reach very high surface density and a central starburst. This central starburst is going to consume a lot of gas at the center and also drive a strong outflow. So after the maximum of this compaction event, we see a quenching phase in which the gas we see mostly disappear from the center. Again, through gas consumption and outflows, we see some ring around the bulge that can form a disk around the bulge, which is very massive at the center. So this is the effect of compaction and quenching. So here, clamp migration is just a signature, because you see clamps here, is a signature of the compaction, of the inflow of gas to the center. It's a signature of the instability that drives compaction. So now within the VELA simulations, we have a new set of simulation with the same initial conditions with a different model of feedback. So now we are adding a model of kinetic feedback. So we can compare now the same initial conditions with two sets of feedback models. So with these new sets, these giant clamps survive feedback. So we can see these massive clamps here and there. So they move around, so they migrate, but there are some differences. This is one example, the same galaxy, the stellar mass and the stellar mass on the right, the gas surface density on the left. But you see these two different models of feedback. So the gas looks very similar, but notice these very compact and round clamps that are mostly stellar clamps. You can see very well in the surface density of stars. These mostly stellar clamps are gone in this new model of feedback. Here in this case, feedback is stronger, is able to drive a strong outflows, and the star formation rate within the clamps is less strong. So the clamps are mostly gas-rich star-forming clamps. So we see little migration of stellar clamps to the center. The migration now is even more gas-rich. That has a strong implication for the galaxy images. This will be more conservations in the rest frame UV on the left, so the galaxies are always clumpy in the UV, but now we focus on the James Webb. We're expecting to see for the first time the red frame I band, a high redshift 2 or so. This will be a typical infrared band. So in this case, with the old simulations, we see these stellar clumps that they are gone in the new simulations. So the new simulations, so the prediction is that in the red frame infrared, the clumpy galaxies are less clumpy. So the clumpy galaxies in the UV are very smooth in the infrared, in the red frame infrared. That's the prediction. But compaction is robust against a feedback. We see the same kind of phenomena, the same kind of L shape in this diagram. So this again is the specific star formation rate versus the sigma 1, the surface density within 1 kpc. And we see the same kind of phenomena in the old simulations and in the new simulations. There are still inflow of gas out to the center. Now here we see the inflow of gas is even more relevant, it's even more important. So we are comparing the evolution of the mass within 1 kpc. So this is one mass of the different components as a function of time for the old simulations and the new simulations. Focus, for example, of the growth of the stellar bulge, this red curve. So in the old simulation, the stellar bulge was continually growing. But here in the new simulation, we see a strong step there. So here in less than 1 gigayear, more than 90% of the stars in the bulge are formed through this burst of star formation. So it's basically young stars that also trace the gas within 1 kpc. So this is the compaction event. Some point there's a lot of gas going to the center and that drive this burst of star formation. Very concentrated in time now than before. And here there are no mergers involved. There is no mergers at this epoch that we found in these simulations. This is all in situ growth of the bulge in this case. Now the feedback is able to regulate the star formation in the disk, so the gas fraction is higher, means that the gas inflow is much higher, that drive even a stronger inflow event than before. Before it was much fainter. So this is the main compaction event. So the summary of this talk, we are now analyzing a new set of simulations, VELA 6, with a new models of feedback, especially with the addition of injection of momentum from the expansion of unresolved supernova shells. So basically it's a kinetic feedback mode with the same initial conditions. So we are able to compare different models of feedback. We found the galaxy compaction and migration of clumps are mostly driven by violent instability. These giant and massive gas-rich clumps now migrate, or they move around the galaxy. And compaction is a robust process. This very happens in all these massive simulations. And we found fast inside-out quenching achieved through compaction and outflows. And finally, about this question, we found that compaction is something ubiquitous in all these massive star-forming galaxies. So it's a fast and robust process for gas formation, particularly massive gas-rich galaxies at high redshift. So that's all. Thank you.